Good afternoon, good afternoon. Welcome, welcome, welcome. This is another paper that I also use for one of the lives that I did on the 4th of November for the grade 11. So I'm going through it so that at least you guys, you can have access to this information. I just want to emphasize, guys, when I'm doing these papers, I'm moving from the assumption that you have covered some of this stuff and you have an idea of what this is all about. So I'm assuming that I'm dealing with people that have got a base of the knowledge in as far as the content in grade 11 is concerned. So in as much as I will be explaining, but I won't go that deep in giving explanations. I'm more into helping you to have that critical mindset when you are analyzing or when you are going through the question, which help you to prepare for the exam, which helps you also to prepare for the test. So this is what I mostly focus on. But that does not mean that I cannot explain to you some of this concept, but I'm moving on from this premise. I expect you, before you go through some of these videos, just go through the content so that when you get to listen to some of my explanation, then it can make sense. Because to someone who is not knowledgeable enough in as far as this content for this grade is concerned, it can be difficult. But I try by all means to give as much information as possible. So let's go through it now so that we save time. So the first thing that we have got question 1. Complete the statements in column A with the options. In column B, write only Y or Z next to the question numbers 1.1.1 to 1.1.8 in the answer book. So this is what we have. This is what we have. It's not something that is complicated, guys. These are the concepts that are covered in the first part, where you look at your revolution, you look at your rotation, you look at your unequal heating of the earth. Of course, those are some of the things that are involved. So let's go through it now. Incoming solar energy reaching a given area, what is it called? That is your insolation. Insolation simply means incoming solar radiation. That's what it's all about. So that is your Z here. It's incoming solar radiation. Okay, insolation, terrestrial radiation. This is the long wave radiation that is radiated by the earth. Of course, that's terrestrial. So the correct answer there is insolation. The manner in which the heat is evened. This should guide you. Evened, which means something is balanced. Which means what comes to your mind is what? Is your energy balance. When you talk about the albedo, we are talking about the fraction of deflected radiation. That's what albedo is, fraction of deflected energy. Okay, heat energy, that's your albedo. So this one now is your what? Energy balance. From the word evened, we are talking about something balanced. Okay, then the earth turns around its imaginary axis once every 24 hours. That is your rotation when the earth is spinning on its axis. Okay, that gives us a day. Okay, 24 hours, that is your rotation. Okay, the time of the year when midday sun is directly overhead at one of the tropics, 1.1.4, that is your solstice. Remember, we talked about the solstice mostly. Solstice, basically time of the year when sun is directly overhead one of the tropics. We talked about the solstice, where we're saying that during the solstice we have got what? We have got winter solstice and summer solstice. Winter solstice, it simply means that the nights are longer than days. Remember, I talked about this. Okay, so this is when the sun is directly over the Tropic of Capricorn. Here is when the sun is direct over the Tropic of Cancer. Your question is saying when the midday is direct ahead one of the tropics. So one of the tropics, obviously, Tropic of Capricorn and Tropic of Cancer. So that is your solstice. It can either solstice, of course, when it's directly over the Tropic of Capricorn. Here we have got what we call the summer solstice, when the day are longer than the nights. Here we have got the winter solstice, when the nights are longer than the day. That's basically what we are talking about. Okay, so that's solstice day. Circulation pattern of the on a global scale. That is your global air circulation. But you also remember when we did the 2024 paper, there was also another question that talks about the primary circulation. There was another person that also talked about primary circulation. Do you still remember this? We also defined the same way as global air circulation. So I'll take both as correct. But mostly this global air circulation is more or less the same thing, so I would take both. Then the next one, the difference in air pressure causing air to move from high to low pressure. That is your pressure gradient. That is your pressure gradient. Okay, Coriolis force is a force that deflects wind to the right in the northern hemisphere, then to the left in the southern hemisphere. That is your Coriolis force. Zones of high pressure and low pressure areas found at different latitude. These are the pressure belts. Remember, we're talking about these, okay? The zones of high pressure found at different latitude. These are found at different latitude. This is at 0 degrees latitude. Subtropical high is at 30 degrees north and south latitude. And then subpolar low is at what? 60 degrees north and south latitude. Then the polar high is at 90 degrees north and south latitude. So the answer there is pressure belt. Then the cell of air circulation that occurs between 30 to 60 north of this. The cell that occurs between 30 and 60. So we are saying now, let me get something that will actually explain that one. Let me see if I got something from my notes just to add on that. So basically, we are talking about this cell that is within 30 degrees north and 60, and that is your what? Your Ferrel cell. That is your Ferrel cell. So your Hadley cell, you find it from 0 to 30, Hadley cell. Ferrel cell from 30 to 60. Then from 60 to 90, you have got your what? Your polar cell. That's basically what we are talking about. So the correct answer there is what? Is Ferrel cell. Let's move on to the next one. So this is what we have for 1.2. Refer to the sketch below and answer the question that follow. Choose the answer and write only the letters A to D next to the question numbers 1.2.1 to 1.2.7 in the answer book. What is it that we have here? Okay, what is it that we have there? We have got this, okay? So what should come to your mind, guys, when you're looking at this diagram? Try to be analytical. What comes to your mind, number one, is, of course, when it comes to the ocean, we have got a cold ocean here on this side. That is part of the west coast. Then we have got a warm ocean here on this part of the South African coast. That is your Indian Ocean. That's where we have got the warm ocean. So what are we likely to have in terms of wind? We have got warm Mozambican current. Warm Mozambican current, it is warm and moist. We have got here the Benguela current. It is emanating from the what? From the cold ocean, that is Atlantic. Benguela current is cold and dry. So that's what should come to your mind. In terms, something to do with the ocean currents. That's what should come to your mind, because you need also to be critical when you're looking at this diagram. So the first thing is large movements of water that occur in all the oceans. This is giving you a clue. All the oceans of the world, that is your ocean currents. Okay, the large movements of water. Then the ocean on the west coast of South Africa. Remember, I've already talked about what is on the west coast. This is your west. That is your Atlantic Ocean, which is A. Then the exchange of heat between the ocean, the atmosphere, mainly occurs through the oceans. Obviously, it's happening through the wind. Of course, when it's moving, we talked about your, the wind, the easterlies. We talked about tropical easterlies, your westerlies. But when it is rising now, of course, that is more heat between. They're talking about the atmosphere when it rises. Of course, that is more to do with evaporation. So that is your B there. Let's move on. This is very interesting. Then this is the ocean current that flows along B. Along B, that's where we have got the warm ocean along B there. Can you see? That's the Indian Ocean. We have got the Mozambican. We have got the Mozambican current there, which is warm and moist. Then the next one, the ocean currents plays a combined role in redistributing heat energy by. What does it do? It sort of moderates. It moderates temperatures. That's what the ocean current does. It moderates temperatures. It made them, okay. It stabilizes. It's moderating temperature. That's what it does. The cold Benguela current transfers. Cold Benguela current is emanating from a cold ocean, which means this is out already. It's talking about warm, and this is out. It's already talking about warm. So what it does is a cold air, which means these two are there, but that way from the poles to them, the type of climate that we are likely to have within the area where we have got the Benguela current is the temperate. Remember, the type of rainfall is frontal rainfall, temperate. Remember, when you're doing the climatic regions like your equatorial, like your desert, like your coniferous, which is more like your temperate region, where it rains when it is cold. So that is your temperate, which means the answer there is B. Then warm ocean currents move to the warm ocean currents. Obviously, it's more to do. Remember, when you covered air masses, a large body of air with similar characteristics in terms of temperature and also what moisture content. So since it's coming from the warm ocean, where are we likely to have? Which means this is out in terms of where they move from, because it's supposed to start from somewhere where it's what? It's warm. So it moves from the equator, it's fine, then it moves towards the poles. That is your answer is C. Okay. Let's move on. So now this is the question that we have referred to the sketch below and answer the questions that follow. Obviously, what comes to your mind, guys? Remember, in the answer question paper 2024, we actually talked about what? We talked about the foehn winds. This is the same thing that is happening here. Check here. A, this is part of your windward side where there is warm air that is riding, that is cooled at wet adiabatic lapse rate, which means for every increase in 100 meters altitude, the temperature drops by 1 degree. So this is why it results in the formation of clouds that we have and rainfall on the windward side. But however, the same parcel of air, as it was rising, now it is descending on the leeward side. When it's descending now, it is actually compressed and it heats up, which means it is now moving at what we call the dry adiabatic lapse rate, which means for every decrease in altitude by 100 meters, the temperature increased by 1 degree. So this is going to end up being warmer, which can result in veiled fires, which can result in what we call veiled fires. So obviously on this side, which we call the leeward side, we are likely to have veiled fires, melting of snow. Remember, it's common in the Alps, melting of snow, which can result in avalanches or floods. Okay, those are some of the things that should come to your mind. That's just some of the things that should actually come to your mind. So here, more rainfall on the windward side. This is the windward side. Windward side. This is the leeward side. Okay, which means the higher you go, the cooler it becomes. Wet adiabatic lapse rate. Okay, the lower you go, the warmer it becomes. That is your dry adiabatic lapse rate. That's basically what you're talking about. Does the wet adiabatic lapse rate okay at A or B? You can see that this is where temperature drops with an increase in height. That is your wet adiabatic lapse rate. So that is A, is happening there. Then classify any two natural disasters that foehn winds or other similar kind of winds can cause. The natural disaster, we are talking about your floods. Remember, I said it is associated with high temperatures, veiled fires, which means it's likely to melt snow, which can result in floods. So we are talking about the floods. Okay, that's a natural disaster. We are also talking about the droughts. That's something that can actually happen as a result of these foehn winds. What else can happen? The veiled fires. The veiled fires, okay? This is something that can also happen, okay? The avalanches, these are some of the natural disasters that can actually happen as a result of the foehn winds, okay? Why is the foehn wind? Why is the foehn wind an example of a regional wind? Where does it take place? It's not common in all the areas. They are small area, okay, where this takes place. So we are saying now the foehn winds are dry, warm winds blowing from the interior to the coast. So which means they happen in small areas, okay? They blow from the interior towards the coast. Like think about your berg winds. Think about your berg winds. What happens? That happens mostly in South Africa, where we have got veiled fires, of course. So they happen in small areas. That's why we call them as regional wind. They move from the interior towards the coast. They move from the interior towards the what? The coast. That's why we refer to as the regional wind. Okay. Explain why no rain occurs on the leeward side of the mountain. So we have said that the same parcel of air that is moving upward, it has lost most of its moisture on the windward side. That's why there's no rainfall here. Because when it is rising at wet adiabatic lapse rate, it cools, condensation takes place on the windward side. So it means when it reaches here on the leeward side, it has lost most of its moisture. That's why there is no rainfall that takes place there. Then secondly, when it is descending, it is compressed and adiabatically warmed, which means the moisture that is still within the descending air is evaporated. Hence, there won't be any clouds formed. There won't be any clouds. They're likely to be temperatures increasing with a decrease in height, which result in veiled fires. So that's why we do not have rainfall at all on this leeward side, which is B. Then state measures that can be measures to reduce veiled fires by foehn winds. What measures can we put in place? What measures can we put in place? We can maintain fire breakers. We can establish fire bells, awareness campaigns to encourage fire safety. We can keep an eye on weather warnings to understand whether we are likely to have these foehn winds. We can also encourage disposing to encourage safety measures. We can install also early warning systems. Those are some of the things that we can actually do in Oza to reduce the fires that are caused by the phone winds. That's what we can do. Let's move on to the next question. So now we are moving on now to 1.4, 1.4 synoptic weather map. Remember from the paper that I did first, we also covered synoptic weather map, and on that synoptic weather map, we also showed you how you can come to say this is winter or this is summer. So let's go through this one. So as you can see on this synoptic weather map, the first thing that you see, can you see how close your cold front is to Cape Town? So that in itself already tells you that it is what? It is what? It is winter. That already tells you it is winter. Then the other thing that you can also see, you can see also we have got the H, which is the high pressure in the interior. Then we have got the coastal low at the coast. So that also tells you that it is what? It is winter as well. That's what tells you also it is winter. We can also see the weather conditions at Cape Town. You can see 3/4. Of course, not overcast, but you can see that there's cloud cover. You can also tells you that they are likely to have rainfall in Cape Town. And when do we expect rainfall in Cape Town? It is rains when it is cold, which is in winter. So that in itself, it actually substantiates or it supports that it is indeed winter. That it supports that it is indeed winter. Okay, I would say also in the interior, there are clear, calm conditions. We are supposed to see the overcast in the interior. It shows that is stable weather condition, but you can see it calm and clear in the interior as well. So this is how you can analyze to know that it is winter. So this diagram is a typical winter. Why? You Cape Town, there's rainfall. It rains when it is cold, winter. Look at the position of your what? Of your cold front. Look at the position of your mid-latitude, the way it moves from driven by the westerlies from west to east. You can see the way it's moving, and also the presence of your high pressure in the interior. That's what shows you that it is indeed winter. Okay, let's move on now. Determine the pressure at B. What pressure do we have at B? That is 1,012 hectopascals. You can see 1,012 hectopascals at B there, 1012 hectopascals. Okay, provide a term given to area D on the map. A term given to area D on the map. What is the term that is given? D, remember we have said that an area of constant pressure between two high pressure systems. That is your saddle. That is your saddle. That is your saddle, an area of constant pressure between two high pressure systems. That is your saddle. Here we have said that is 1012 millibars or hectopascals. Okay, hectopascals, okay, HPA. Then give evidence from the synoptic weather map to prove that feature C is a low pressure. Feature C is a low pressure. What evidence is there? There is an L there. There is an L that shows it's a low pressure. You can also look at your isobars. Okay, the pressure here you can see is lower and it increases. The pressure increases going outwards, which means there's low pressure where its L is, then it increases going outwards. That's what also shows that it's low pressure. Okay, the synoptic weather map represents winter. Provide evidence from the map. What evidence? Evidence that you can get from the map is the cold front. The cold front that you have here, the mid-latitude or just the cold front in general, it shows that it's winter. You also have the cold front, the coastal low that is ahead of the cold front. In summer, you usually find it here. But here, the coastal low is ahead of the cold front. It shows you that is what? It is indeed winter. The Kalahari High over the interior, you can see the Kalahari High here over the interior. You can also see the position of your high pressure system, your South Atlantic and South Indian High. They have moved further north. Why? Because of the shifting of the intertropical convergence zone. They follow the shifting of the intertropical convergence zone, which is now in the northern hemisphere. So that's what you can also talk about. Clear skies on the interior, it's not cloudy, it's not overcast, so that's what supports that it is indeed winter. Okay, then determine the weather conditions experienced at A. What do we have at A? The cloud cover, that is 3/4. You can see that is 3/4 there. That is the cloud cover, 3/4. Then the wind direction, you can see this tells you it blows towards this direction. This is where it's heading to. If you're looking at this, okay, shows where it's heading to. This is where it's coming from here going towards that. So we call it, name the wind according from where it's coming from. It's coming from here going towards this direction. That is a northwest wind. That is a northwest wind. Okay. Then dew point temperature, this is your air temperature. okay, which is 18 degrees. This is your dew point temperature. That is your 13 degrees Celsius. That is your dew point temperature. If you want to further analyze this, you can also see that the 10 knots is the wind speed. That's the wind speed, 10 knots. If it's like this, then that is 5. That is how you see your 5 knots. But if it's starting here, that is your 10. Then if it's 15, it's going to be like this. The long one and the short one, that is 15. That's how it's done, okay? Comment the pressure gradient at E and the resultant wind speed. At E, what do we have? What do we have at E? The pressure gradient. You can see the isobars, they are very close to each other, which means it's a steeper pressure gradient, which shows that they are strong winds. Steeper pressure gradient, when the isobars are very close to each other, it shows that it shows strong winds, which means that the isobars are very close to each other, it shows strong winds. That's what it means. And when the isobars are far spaced, it shows what? Gentle winds, which means they are light winds. That's what it shows. Okay, Janko. Let's move on to the last one, 1.5. Read the extract below on the effects of drought and desertification in Harigwala District Municipality. Drought and desertification in the Harigwala District Municipality, KwaZulu-Natal, impacts communities through reduced water availability. These are the impacts now: reduced water availability, diminished crop production, and loss of agricultural land. This is leading to food insecurity and potential migration to urban areas. These events also cause increased run-away fires, high erosion, and loss of species and habitats. Okay, so what is needed now here, guys, is the focus is on desertification. What is desertification? That's what is needed. The process where once fertile soil becomes arid, the spread of desert-like climatic condition. That's basically what we are talking about. Of course, that's desertification. What we have within a desert, of course, little or no rainfall, little or no vegetation. When those conditions are spreading, that's desertification. That's basically what we are talking about. Okay. Then quote from the extract: environmental impacts caused by the events of drought and desertification. What is the environmental impacts caused by the events of drought and desertification? We are quoting from the extract. What do we have? We have got loss of what? Agricultural land. We have got diminished. We have got loss of agricultural land. We have got environment. Okay, we are focused on environmental impact. So we can talk about, okay, number one, okay, 1.5.2, we can talk about what we have here. Loss of agricultural land. That's what is there. From the extract, what else do we have? We are likely to have high erosion. We are likely to have increased runaway fires. We are likely to have loss of habitat. We are likely to have reduced water availability. So those are the environmental impacts that are caused by the events of drought and desertification. Then outline the natural causes of desertification. What are some of the natural causes of desertification? That is 1.5.3. Climate change is one of them. Global warming and shifts in weather patterns can worsen desertification. Global warming, this is the increase in temperatures that result as the emission of gases into the atmosphere. That is your global warming, because to be specific, especially like your carbon dioxide, methane, and other greenhouse gases, okay? That's what causes global warming. So it's likely to cause climate change. Global warming and shifts in weather patterns can actually worsen desertification. We are likely to have also 1.5.3, the causes: the prolonged periods without rain reduces vegetation and soil moisture, leaving the soil vulnerable. Because we are now talking about the once fertile soil becoming arid. So if we have got prolonged periods without water, it actually reduces what? The vegetation and soil moisture, which leave the soil to be vulnerable. High erosion, okay, what else? Loss of topsoil leads to soil degradation. Uncontrolled fires can destroy vegetation, leading to increased soil erosion, increased erosion. Those are some of the things that you can talk about in as far as the causes are concerned. Then the last thing, recommend 3 management strategies to reduce desertification. What can you recommend to reduce desertification? What can you recommend to reduce desertification? We are now talking about the recommendations to reduce desertification. Practice land management. That's what you can do. Practice land management. Of course, practice land management, restoration of the area, reforestation, which means we are planting more trees. That's what we can do. We can also enhance soil fertility, maybe through using organic fertilizers like your animal manures and things like that. Of course, allowing also the green, the leaves from the plants to decay to form humus that can also help improving the soil fertility. Okay, reduce the size of the cattle heads to work within the land carrying capacity. We are reducing we want to try by all means to reduce overgrazing. That's what we are trying to do through rotational grazing and other means. Explore other income generating activity that is less impact on the environment. That's what we can do in order to reduce desertification. That's what we can do. I think this takes us to the end of question 1 that covers climate and weather from the 2025 paper. Thank you.